So last time we did a little bit of review and we talked about solving right triangles, which is something that we would have done in our geometry course a long time ago, but we reviewed how to do that again. And then we started extending these ideas of, okay, if we don't have a right triangle, what can we do? Because we lost all of the tools that we were using in the right triangle situation can't be used in the non-right triangle situation. So we started developing these new ideas. We said that the two main tools that we're going to use are going to be this law of sines and law of cosines that we talked about yesterday. And we talked about these distinct situations that were reminiscent of the triangle congruence theorems that we saw in geometry, about when I should use which theorem, whether I should be using angle side angle is a law of sine situation, or side angle side is a law of cosine situation. You guys kind of remember that from last time? Yeah. So let's go and start here. I noticed when I thought about what we did last time, I'm like, well, you know what we probably should have done is draw some pictures and make sure we can differentiate between like angle side angle and angle side and that kind of stuff. So let's take a few minutes and do that real quick. So here is, I'm just going to draw some pictures. So here's a situation where we've given two angles and a side. The stuff that I've highlighted are the givens. Just, yeah. Yeah, is this angle side angle or angle side? This is angle side angle. I can tell that it's angle side angle because the given angle, the given side is a part of both angles, right? Now, contrast that with angle side, where the given side is a part of only one of the angles. Paul?
Yeah, so the angle on the right is not part of the side, and if I kind of, where I'm telling it apart is I'm like reading it, I see angle, and then side when I like lay it flat.
Sure.
I don't really know if that's...
Yep, that's the same idea if you're following like consecutive pieces.
Yeah.
Yep, you can think about it that way too. That's okay. But it's one of these things like once you've seen it, it's like, okay, I can visualize. So if you try to describe like what is this, the difference between the two, that gets a little complicated.
Right. To
make sure you're saying something technical. I'm just going to draw the pictures and we'll talk about it because that's all we really need, right? We're not proving anything, so we don't need like a real tight verbal description. We just need a visual understanding of what's going on. Okay, here we have two sides and an angle. Is this side angle side or side angle?
That's angle side. No, side angle side.
That is side angle side. Again, what I'm noticing is that the angle is made up by the two given sides. So side angle side is going to look like this, where one of the given sides is not part of the angle. So that's side angle. And the one that nobody ever screws up is this one, which is definitely just side, right? There's nothing confusing about what that is. Any questions about those guys? Okay. Again, the two that are critically important that you're able to tell the difference between is the side angle side and the side angle. Because one of those we should use the law of sines, the other we should use the law of cosines. Now, if we look at these five situations and we compare them to the triangle congruence theorems we had in geometry, one of these doesn't fit. Which one of them doesn't fit?
Side.
Side-side angle is the answer. There is no congruence theorem in geometry for side-side angle. And the reason is you can have side-side angle congruence and not have triangle congruence. So let me demonstrate kind of what that looks like or why that's happening. So I'm going to do this geometrically. I'm just going to kind of construct a picture because it's kind of difficult to draw this in such a way that's really clear. So I'm going to draw a situation where I have a side length of 10, 12, and then a 48-degree angle, and show you that I can make two triangles out of this. Okay. And so now I need to draw in the 10 degree or the 10 unit length side to complete a triangle here, right? So the way I'm going to do that is I'm going to make a circle here centered at A with a radius of 10. And any place that circle intersects that line that we draw is going to give us the triangle that we're looking for. So you notice that it intersects once up here. So if I make the triangle ABC, I have a triangle who has side length 10, 12, and then a 48-degree angle, right? But I also notice that the circle intersects that line over here at point D. So if I make the triangle DAB, I also have a triangle who has a side length of 10, a side length of 12, and a 48-degree angle. What we've just demonstrated here is that side-side angle congruence does not guarantee triangle congruence because we have two triangles that are distinctly different triangles that have side-side angle congruence, right? Everybody can see that? So what does that mean for us now? It means that in this side-side angle situation, we're going to have to be very, very careful. Because depending on what this angle is, we might get two triangles like we've had before. But as this angle gets bigger, these two lines here that divide or that indicate the two separate triangles are going to get closer and closer together. And they'll actually become the same line when that angle is 90 degrees. So when that angle is 90 degrees, you actually do get triangle congruence. You guys had a special name for that situation. You had a special name for that situation, a theorem in geometry. I think your textbook calls it the Hypotenuse Leg Theorem, if that rings a bell. That's a special case of SSA where the angle has to be 90 degrees, where it guarantees you there's only one way you can construct a triangle with those dimensions. You can't get two like we could here. And if we keep going, if that angle gets bigger than 90 degrees, then the circle doesn't intersect it at all, right? So those 2 points are getting closer and closer and closer together, the B or the C and the D, until they become 1 point at 90 degrees. And past 90 degrees, they don't intersect at all. Does that, you guys kind of see that? So let's go through and kind of work that out formally. We've got a geometric notion of kind of what's going on here, but let's kind of work that out a little bit more formally so we can talk about this SSA condition or situation with a little bit more detail, a little bit more thoroughly. Okay. Let me check something real quick about yesterday. I did think, okay, yeah, we did do an example. Okay, good. I was pretty sure we did, but I just wanted to double check. So sometimes this SSA situation is called the ambiguous case. Because as we just demonstrated there a moment ago, we can have a situation where we have two triangles, one triangle, or zero triangles. So we have to be a little bit careful there about what's going on. So for the sake of argument, let's say that we have this triangle ABC, and since it's an SSA situation, we're given angle A, side AB, and side BC. Everybody's cool? Okay. Now, this starting information is going to break down into three cases. The first case is if angle A is obtuse. When we say an angle is obtuse, what do we mean? Bigger than 90 degrees and less than 180, right? Because it has to still be part of a triangle or whatever. Everybody's cool? Okay. So if A is obtuse, what does that mean about, what can we say about BC then? The side BC?
Has to be acute.
Well, side lengths aren't acute, right? Amy? Great. It has to be the hypotenuse. It has to be the longest side, right? We know that because there can't be another angle bigger than angle A, because a triangle can't have two obtuse angles. There's only 180 degrees in a triangle. You can't have two of them bigger than 90. So guarantees us that BC must be the hypotenuse. Yes, sir?
So because it's across from A, it's going to be the biggest stuff?
Yes.
Gotcha.
Yep. Because the side lengths and angle measures are proportional in a triangle. So the biggest side is across from the biggest angle, the middle side across from the middle angle, smallest across from the smallest. Yep. So if we then can say there's three situations for the two sides that are given. Either BC is small, I don't remember which order I want to do this, is bigger, BC and AB are the same, or BC is smaller than AB. Now, BC has to be the hypotenuse, right? So in this situation where it is bigger than the other side, we're just going to form one triangle. That's fine. We can make a triangle. It's one triangle. If BC is equal to AB, that can't happen because BC has to be the hypotenuse, right? So if I just list information in an SSA situation and A is obtuse and BC is the same side as AB, well, I can't make a triangle out of that. Same thing as if BC is smaller than AB. Again, BC had to be the hypotenuse. If you gave me it listed where it was shorter than the other side, well, I can't make a triangle out of that. Everybody feel okay on this? Very common sense. You had to think about it a little bit, but it's like, okay, makes sense. So the next situation is if that given angle is 90 degrees. Is there anything different if that angle is 90 degrees versus obtuse? No, right? Still forces BC to be the hypotenuse. You can't have a triangle with a right angle and two right angles in it, or a right angle and an obtuse angle. So we still know that BC has to be the biggest side, so we can still say the exact same three things about the side lengths, that BC has to be the longest side, or no triangle can be constructed. Everybody feel okay on that? So case 3 then is where angle A is acute. What do we mean by acute?
Less than 90.
And?
Has to be 180.
Greater than 0?
Greater than 0.
Right? So between 0 and 90. Again, can't have negative angles in a triangle. We've certainly seen we can have negative angles, right? We defined what a negative angle means in a trigonometric sense, but here we're operating in a, like planar geometry, and there's no negative angles in that world. Yeah, like in the, so. Okay, so those three situations still exist. So it turns out that here there's always going to be those first two situations, if BC is the biggest side or if it's co-equal to AB, just one triangle can be formed. The confusing place is if that side BC, the one opposite our given angle, is the shorter of the two sides. Then there's some ambiguity as to what's going to happen. You could have 0 triangles possible there, you could have 1 triangle possible, or you could have 0 triangle, or 2 triangles possible. So the natural question here would be, how do I tell whether I have 0, 1, or 2? If I can't do it just by looking at, the given information, what do I need to do? There has to be some way to tell. This is the trick. So if we go back to our given here and we construct a law of sines, we could say sine of A over BC should equal sine of C over AB. You guys agree with that? Just using the law of sines, I can write that. So angle C is the only piece of that I don't know, right? The other 3 pieces were given information to me. Everybody agree? So what I'm going to do is I'm just going to solve for angle or for sine C. I'm just going to cross multiply and divide to get the sine C part by itself. So I cross multiplied, and then we divide by BC. And this number is going to tell me whether I have 0, 1, or 2 triangles. If that number is greater than 1, I get 0 triangles. If that number is equal to 1, I have 1 triangle. If that number is less than 1, I end up with 2 triangles. Now, the way I like to think about this is really just, it's the longer side times sine of the given angle divided by the shorter side. That to me is a heck of a lot easier to remember than like the other formula with the A's and B's and all that crap all in it, right? So let's do some specific numeric examples where we kind of see this in play. Everybody's good with that? Just FYI, I think this is the most difficult thing we do this chapter, is dealing with this SSA situation. While it's not like a difficult calculation to do, there's kind of a lot to remember in terms of like what happens when this happens or that happens or whatever. The only one that's really the non-common sense one is where A is acute, where the given angle is acute. So let's say we want to solve the triangle where angle P is 56 degrees, side P is 16 units, and side Q is 19 units. So we should start by drawing a picture. So definitely one of the angles needs to be named P because we have an angle P. And another angle needs to be named Q because I have a side Q. What do you want to name the third angle, though?
R.
I'm going to name it R because it's the alphabet. Thank you, my pirates. Because you all said R as a joke. Yeah, because pirates are awesome, right?
Because they got better voice acting.
Yeah,
Probably.
probably.
We're not Robbie Rottens.
Okay. So we have, there's our picture, right? So what situation are we in here?
Oh, that's it. Oh, sorry. Go ahead. Sorry. We can't add up to 180, obviously, but we can probably use the P's, both the side and angle of P, to get the angle of Q.
First thing we need to do is figure out what situation we're in, whether it's angle side angle or side angle side or side side angle. This is side side angle, which tells me we're going to be using the law of sines to do this problem. But in the side side angle situation, we have to check a couple of things first to figure out even if this problem is possible, or to figure out how many triangles we're looking for if it is possible. So the first thing I'd want to do is check the size of the given angle. That given angle is acute. So that's a potentially dangerous situation, right? When that given angle is acute, the thing I need to worry about is comparing the side opposite that angle to the other given side. In this case, 16 is less than 19. Everybody's good there? This is that situation where we can have 0, 1, or 2 triangles. So we need to check that. The way we check that is we take the longer side times sine of the given angle divided by the shorter side. Let's pound that through our calculator. As a quick reminder, what mode should my calculator be in to do this? Degrees. How do I know degrees?
Because you're working with degrees.
Yeah, the problem, the angles in the problem are given as degrees. When I do that, I get 0.984. And since that's less than 1, I know that I'm going to be looking for 2 triangles here.
Uh-oh.
So this is the most complicated situation that we're going to run into. You guys good with how I reasoned through doing this, though? So first I found it was SSA, then I looked at the size of the angle. Since the angle was acute, I compared the two sides that were given, and it fell into the worst possible scenario for us, where we got to do a little bit extra to figure out what's going on. Okay, so one of the things that I'm going to make sure that I do when I run into a two triangle situation is I want to make sure that I'm doing a good job of keeping track of my answers. So I'm going to make a space for the answers for triangle 1 and a space for my answers for triangle 2. Now, because I have two sets of answers for the unknown stuff, I'm going to use a subscript. So I'm going to use 1s and 2s to indicate whether they're part of the first triangle or second triangle. So I'm going to have angle Q1, angle R1, and side R1 in triangle 1, and angle Q2, angle R2, and side R2 in triangle 2. Everybody okay with that idea? Again, from my standpoint as a teacher, I see lots of students that have trouble with this just because they don't do a very good job of keeping track of their work, and they use the wrong answers for the wrong stuff, and turns into kind of a mess just because they lost track of what they were doing. So I'm going to make sure that I organize my paper pretty clearly so I can tell what work goes with what. So now that I've wrote a space for both sets of answers, I'm going to divvy up and make a column on my paper and do the work for triangle 1 in one column and the work for triangle 2 in another column. Everybody's okay with this idea? And now you can go back and forth working in each column. I would not. I'm just going to do all of triangle 1, and then I'm going to do all of triangle 2. Again, it feels like there's less opportunity for me to make a mistake in using the wrong information, the wrong context if I do it that way. But you don't have to do it that way. That's just what I like to do. Okay, so I'm going to start with the law of sines. So I have just that sine of P over P is equal to sine of Q1 over Q. And I know I have to start with angle Q because I don't know anything about angle R or side R, right? So the law of sines wouldn't help me immediately solve that. I have to find angle Q first. So we'll cross multiply. So that gives me 16 times sine of Q1 equals 19 times sine 56. And then I divide both sides by 16 to get the sine of Q1 by itself. And then how do I get rid of a sine in front like that? Sine inverse, very good. So Q1 is going to equal sine inverse of 19 sine 56 all over 16. Now it's calculator time. So this is another situation. I'm going to use the fraction command on my calculator so I don't have to worry too hard about the parentheses. I can just kind of write it exactly like it looks like on my sheet of paper. And I don't have to think too hard about things. So I get 7989 as my answer there. I'll record it up here while I'm at it. Now that I have Q1 Getting R1 is really easy, right? Because now I have two of the three angles in my triangle. So 180 minus 56 minus Q1. So 44.11. Everybody feel good so far? And now that I have angle R, I can use the law of sines to solve for side R. So sine P over P equals sine R1 over side R1. So to solve, I'll cross multiply. And then I'll divide by sine 56. If I go to my calculator, I have 1343. So this, to get the values for the first triangle, was not any different than what we did yesterday in our example, right? This is all still the same. Nothing really different. I mean, you have to use a sine inverse or whatever, but like big frickin' whoop, you know?
I do have a question about that.
Sure.
So why did you use a sine inverse there and not here now?
Well, I'm solving for R,
Right.
a side length. Over here, I was solving for angle Q1.
So when you're solving for the angle, you're always going to do sine inverse?
Yeah, of course, because the inverses give us angle measures,
Okay,
right?
gotcha.
It's like the Sokotoa's version of going from radians to degrees for a rough analogy.
Or go from side lengths to angles, yes. Yeah. Yep, same idea. Okay, so triangle 2. How do I get started on here? Obviously, if I can get one of the two angles, I'm good to go. Well, here's the trick. Q2 is always going to be the supplement of Q1. It's actually easier, I shouldn't say, it's less computation to get the second triangle, because to get the first angle, all you need to do is a little bit of subtraction. So that's 100.11. That's a heck of a lot easier than having to do the law of sines again, right? And that's lovely, because now to get R2, well, I'm just going to be doing that, right? 180 minus 56 minus my previous answer. So that's 2389. And then to find R side R2, I'm going to set this up the exact same way as the previous one, but I'm going to use the value for angle R2 instead of the angle R1. You know what I mean?
Go.
So that second triangle is actually, in a lot of ways, way easier to get, or way less work anyways, than the first triangle was. The tricky part was recognizing that you needed to do it. That tends to be the hard part. So 782. Let's go record those real quick. 100.11, 2389, 782. I'll scroll back down so most of us are looking at the work. But that's really as long as any of these problems can get, is the two triangle situation. But the second triangle isn't so bad, right? I'll tell you right now, the place where if you get hung up on this, getting the second triangle started, it's remembering that very first step.
So if it's a no triangle situation, what would you put?
Just that there's no triangle possible. So let's look at another example here. So here we have a 74-degree angle A, a side A that's 2.5, and a side C that's 4.9. So obviously I have angles A and C. I'm going to name the other one B because the alphabet. So there's my picture. Everybody cool? What situation are we in here?
Oh, we're in the side angle.
Yeah, we're in the SSA situation, so we need to be using the law of sines. The next thing I need to check is that angle that we're given. 74 degrees is my angle, so that's acute. All right. Then I need to look at the side opposite that angle and compare it to the other given side. So here, side A is smaller than side C. That was the 0, 1, or 2 triangle situation. Okay. I see where you're going with this, Mr. Kulik. So we're going to do the longer side times sine of our given angle divided by the shorter side. And that comes out to be, oh my goodness. Great googly moogly, Mr. Kulik. Why did you write sine 56 in the denominator? It's because you're still doing the previous problem and you weren't using your noodle. And why did you type 49 and not 4.9? Well, also because you were talking and going too fast. clearly. Okay. There we go. So we get 1.88 when you type that in correctly. What does that mean? Since that's greater than 1, there's no triangles possible, so I'm done. I just acknowledge that there's no triangle possible, and there's nothing to do. There's nothing to solve for if there's no triangle.
Correct.
Cool.
I like it.
I'm happy with that, right?
No problems.
Yeah. Give me less problems in my world, and I'm happy, right? One less thing to do. How do you guys feel about this SSA situation? Once you figured out whether you're looking for 0, 1, or 2 triangles, it's not so bad, right? The hard part is just figuring out what's going on. Okay. Just FYI, if you had messed something up, it's this part that would get you into trouble. So if you had incorrectly determined whether you had 0, 1, or 2 triangles, and maybe even you forgot to do that altogether, if it was a 0 triangle situation, that's going to give you an error. It'll give you a domain error on your calculator when you try to do that computation. So just FYI, if you're doing your homework and you're like, why isn't this working? Why do I keep getting an error? It's probably because there's no triangle possible. Just FYI. If it was the 1 triangle situation, that would come out to exactly 90 degrees. So when you find the supplement of it, it's the same set of answers as the 1 triangle. So even if you mess up or you don't remember the 0, 1, or 2 criterion, if you just go bowling ahead right away into the problem and you recognize like, oh, if I get a domain error, it just meant there's no triangle possible. If I get 90 degrees, it just meant there was 1 triangle, and if I get anything other, it just meant there was 2. Okay. All right. So let's move on out of the side-side angle situation. So let's look at this situation. So our triangle angle A is 34 degrees, side B is 14 degrees, and side C is 17 degrees. Well, I guess it's picture time here. Pretty obvious that the angles are going to be A, B, and C. So this is side angle side. That tells me I should be using the law of cosines. So, oops, I guess I forgot to write the A there. So the piece that I'm going to be solving first with the law of cosines is the missing side. So I'm going to say A squared is equal to B squared plus C squared minus 2BC times cosine A. Everybody feel good there? To get the A by itself, I'm just going to square root both sides. And if it's me, I'm not going to do any intermediate calculations, because really what would probably happen is I just screw up some order of operations thing. I'm just going to let the calculator handle the whole darn thing for me. Emma? Absolutely. No problem. Don't forget to do the square root, though. That's a place where every once in a while I see a student just forget to do that, and they get some bonkers crazy answer. It's like, did you really think that a triangle with side length 14, 17 could have the third side length of like 4,000 or something? Like, really? You didn't stop and think about that for a minute? You know what I mean? Sometimes we just get going too fast. So 9.51. Everybody feel good here? So now we're going to solve for angles B and C. To do that, we're going to use the law of sines, because you'll see now that I have an angle and the side that's opposite it. So the law of sines is on the table. Important question. Does it matter which angle I solve for first, angle B or angle C? It does if you want to make sure your life is not complicated. Who wants their life to be complicated? Nobody does, right? So the goal here, when choosing which one to do, is we want to make sure we avoid a side-side angle situation where we can have 0, 1, or 2 triangles. The way to ensure that you avoid that is you find the smaller of the 2 angles first. Which B or C, which one is going to be smaller? B. How do you know that? Because the opposite side is smaller than the opposite side for C. So let's make a note of this. So we're going to always, at this step, use the law of sines to find that smaller angle. Okay. So sine of A over A equals sine of B over B. And we cross multiply. And then divide by 951. And then do the sine inverse. So that gives me 5544. Everybody feel good there? And then to get the last angle, that's really easy because I have 2 of the 3. Oh, 5544. What do you guys think on that? Not too bad, right? The only thing that we really have to be careful about is making sure that you're solving for the smaller of the two angles first. Okay. The last example today. So let's say we have a triangle with side lengths 5, 8, and 10. So which situation is this? Side, side, side. So that's a law of cosine situation. However, before we go diving into the law of cosines, we have to make sure we check something first. We have to make sure that it's even possible to have a triangle with these dimensions. For example, if I list any three numbers, it doesn't necessarily mean that's going to represent something you can make a triangle out of, right? If I say, oh, what about a triangle with side lengths 1, 1, and 100? If you try to picture that in your head, you can see pretty quickly there's no stinking way I can connect those three segments. You know what I mean? Does anybody remember the rule for checking that? This would have been something you might have discussed in geometry. No, it's an easy rule. The sum of the two legs has to be greater than the length of the hypotenuse. How do I know which one is the hypotenuse, Mr. Kulik? It's the biggest one, guys. Every year somebody asks me that, and I'm like, and they're like, what? How am I supposed to? I'm like, it's the biggest one, dude. And they're like, oh, yeah, okay. So 13 is bigger than 10, so we're good. Triangle is possible. Okay? If if R was 15, no triangle is possible. You guys get it? Okay. Now the question, okay, we can do this problem. The question becomes, does it matter which angle I solve for first, P, Q, or R? Only if you don't want your life to get complicated. Who wants a complicated life? Shut up. You do not.
I do.
So we want to make this problem in a way that we can avoid the ambiguous case. The way we can guarantee that is that we're going to find the biggest angle first. Which one will be the biggest angle? Yeah, R, which is because the side length is the biggest. It's 10 is biggest. Okay. All right. So we have 10 squared is equal to 5 squared plus 8 squared minus 2 times 5 times 8 times cosine R. Everybody feel good with what we've done here? Okay. Number one mistake I see students make on this solving is they combine those three things. What's the problem with that?
The problem is going out of the order of operation. You have to multiply the cosine R first.
Yeah,
then you can subtract.
that piece you can't combine because it's a coefficient. Exactly right. Okay? So my suggestion here is don't do any computation. Just start moving crap to the other side. So we'll start by subtracting the 5 squared over and the 8 squared over. Don't add the 5 or the 2 times 5 times 8 over because it's not being subtracted, it's being multiplied. So to move that over, we have to divide. Don't drop your negative sign. That also happens rather frequently. And then we'll do the cosine inverse of both sides. Drake, this was the situation I think you were asking about, right?
Yeah.
And here is a situation where I definitely want to use that fraction command on my calculator because this one, the parentheses are not trivial to put them on your calculator to get it to do it in the order you want it to. But if I just use that fraction command, it'll do it in the same way that I can write it like I just have on my sheet of paper, and I don't have to worry about like getting the parentheses in the right place so the calculator does the order of operations I want it to. So when I do that, I get 97.90. Okay. Now, just like in the previous problem, I'm going to use the law of sines to find one of the 2 remaining angles. Should I find the bigger or the smaller of the 2? The smaller, just like before. Whenever I'm using the law of sines, I want to look for the smallest angle first. When I'm using the law of cosines, I look for the biggest angle first. And I'm doing that just simply to make sure that I avoid those ambiguous cases. But I'll make note of that again. Okay, so we have sine of r over r equals sine of p over p. Cross multiply. And then divide by 10. And then do the sine inverse of both sides. And then it's calculator time. Again, I like to use that fraction command. And I'm using that ands command all over the place rather than have to recopy long numbers into my calculator. So that gives me 2969. And then getting angle Q is trivial because I know the other 2 angles. So 5241. What do you guys think on this one?
Oh, think anymore.
Yeah, I mean, they're not too big of deals, right? For the most part, once you've figured out what to do, the calculation, you're just grinding stuff through a formula and doing some basic algebra, not too bad. The hardest part is making sure you're doing the right thing at the right time.
Right.
Drake, do you have a hand?
Scroll up.
Yeah, sure.
I just need to see if what I wrote down is right. Side, please. Yeah.
This right here?
Yep.
Okay, cool. All right, so this is as far as I wanted to go today. We're going to stop here. At this point, you guys should be able to do 1 through 22 in worksheet 1. I'm not asking for you to do that for Monday because, yeah, we haven't had a chance to ask questions about it. And quite frankly, like, get your school legs under you before you start having to do some homework. I would point out, though, we have one section only remaining in this chapter. So you best believe there'll be a homework quiz next week. It'll either be Tuesday or Thursday. We'll either do section 7.4 and the homework quiz on Thursday or on Tuesday and then review on Thursday, or do section 7.4 on Tuesday and then do the homework quiz and review on Thursday, and then the test will be the following Monday for you guys. Everybody cool with that?
Yep.
The problem set for this chapter is just 1 through 30. There's not a ton of problems in it, so it's not, although some of them can get kind of lengthy, none of them are, like so bad. And 30 is not a bonkers number. But I would certainly take some time this weekend and do a little bit of the start in on that assignment so that if the homework quiz is on Tuesday, you're not caught with your shorts down or whatever. On the homework quiz on the test, I'll give you the formulas for both the law of sines and law of cosines. I would not give to you, though, like the rules about when you use it, or like the rules about like whether there's one triangle, two triangles.
Okay.
That's the kind of stuff that I need you guys to know, or at least be able to cope with.
What will you give us?
I'll give you the formulas for the law of sines and law of cosines.
Okay, so you mean sine of A over Y?
Yeah.
Okay, you'll give us that stuff?
I'll give you the formulas. Yep.
Okay, gotcha.
Mackenzie?
And then will you tell us like if sine equals sine is part of
I will not tell you which one to use in which situation. Although the dirty little secret with that, Mackenzie, is if you try to use the wrong situation, you don't have enough information. So it's like, even if you don't remember that for sure, if you try to use it on the wrong one, it's like I have two variables still. There's no way to get not two variables. So it's not too bad.
Can I get some water?
Yeah, absolutely. Right? If you try to take side angle side and use the law of sines on it, there's no place where you have, both of them, the side and the angle, so you can't really, it becomes pretty clear pretty quick that it's not going to work. You know what I mean, Mackenzie? So, like, I wouldn't go bonkers memorizing that. It's not the end of the world. Because you just don't have enough information to use the wrong one in the wrong spot. But it does waste your time, right? But my suspicion is if you do the homework set, you'll kind of naturally end up memorizing like what to use when. You know what I mean? Yes. Of course you can. Of course you can.
Yeah,